So where we left off last time was we ended up with this picture of how modern systems work, where you have multiple processes at any given point in time that are sharing the machine and controlling those processes, and between those processes and the hardware is an operating system that essentially mediates between these processes and the hardware to get essentially three basic goals. The first one is protection and privacy. So we want to give a private address space to each process so that processes cannot access each other's data. The second one is to abstract or hide away the details of underlying hardware. So we're giving higher level abstractions than hardware provides. For example, we're using files instead of just exposing the raw hard drive, or sockets instead of exposing the raw network card. And finally, for this, the last piece of the puzzle was resource management, right? So the last goal is essentially to control how these different processes share the multiple hardware resources in the system. And so we saw last time that there are three key enabling technologies. First one is this combination of two modes, user mode and supervisor mode. And essentially, supervisor mode has some privileged instructions and some privileged state that is not accessible to user mode programs. And the operating system kernel is running in this supervisor mode. And that's why it has these special privileges and has direct access to hardware. And the second bit is essentially this business of exceptions or interrupts to safely transition from user mode into supervisor mode. Right? So that's what we saw last lecture. Today we're going to see the other big component in terms of hardware support for operating systems, which is virtual memory. And so virtual memory essentially lets us abstract the storage resources of the machine and also implement this protection and privacy feature, essentially giving each process a private address space. Let's see this in a little bit more detail. So essentially what a virtual memory system is providing is the illusion of having a large private address space for each process. So each process believes that it's running alone in the machine, and it looks to the process like it has the entire memory of the machine available. Or at least that it has a certain amount of memory available. And so that's one big feature, but there's another one that we haven't discussed so far, or we didn't discuss last lecture, but it's actually quite important, which is what we call demand paging. So demand paging essentially lets us use main memory, or DRAM, as a cache, main memory. It lets us use DRAM as a cache of disk, right? So essentially, we can support programs that use more data and that access more data than we actually have main memory to support, right? And the strategy that we're going to have is the same thing that we do when we implement caches. We're going to have this primary memory hold a portion of the process's data, and then we'll have some mechanism to go to this lower disk, which is what we call the secondary store, to retrieve data that's not present in main memory. You'll see that there are a lot of similarities between virtual memory and caching. At the same time, there are some key differences that are driven by just constant factors. Some operations are much more expensive, so accesses to disk are much more expensive than accesses to main memory, and so that's going to drive us to quite different designs. But conceptually, it is very similar. Okay, so the price for these two wonderful features is that every access that the program performs is going to have to be translated. We're going to have to essentially perform some operations to convert this address that is in the scope of the process into an address that's in physical memory. And so, just to be more concrete, we actually give three different names to memory locations, of which the two important ones for this lecture are the virtual address and the physical address. And so, but just for generality, let's begin with the machine language address, right? So, what does a machine language address mean? So, if you write load word, let's say x12 0x100, X11, this is the machine language address, right? This is what you write in assembly. The ISA will translate this into what we call the virtual address. And so in this case, it will be 0x100 plus the contents of register 11, right? So it will perform, the processor will perform some operations to compute the virtual address, which we sometimes also call the effective address. And that's sort of what, the address that the program wants to access, that the process wants to access. But what we're going to do is insert this address mapping machinery here to translate these virtual addresses into physical addresses. Addresses that actually are in physical memory, that actually map to the main memory that you have in your machine. And the key the key mechanism here, or the key thing to understand, is that this address mapping hardware is going to be under the control of the operating system, right? So we're going to take, this virtual address over here, translate it into a physical address, and then access main memory with it. Okay, so there are two key mechanisms that we're going to see. First, we're going to look at segmentation, which is a very simple technique that has some drawbacks, so it's not used today, or it's not used frequently at least. And then we'll look at paging, which is what modern systems actually do. So let's start with the simple technique. So segmentation, which is also sometimes called base and bound address translation, essentially implements a very simple mechanism. So suppose that you start with some chunk of memory. So the process has addresses from 0 to 0 FFF. And so what we're going to do is map this set of virtual addresses, this what we call address space, into a contiguous chunk of physical memory, right? So we're going to place it at some starting location, right, in some contiguous chunk. This is what we call a segment. But because we want to have multiple processes, we actually want all the processors, or each process, to believe that its address space starts at address 0. We need to perform some translation, right? Because not all the processes can have their memory starting at physical address 0. And so what we do is essentially we introduce a base register in the CPU, and then we compute the physical address by adding the contents of that base register and the virtual address, right? So some address over here, right, is going to map to the same offset, the same. If you start counting from 0, it will be the same distance, right? But the actual physical address will be computed by adding the contents of this base register. Great. So now this means that we can have multiple processes that all believe that their address space starts at address 0, and yet they're all coexisting in different locations of physical memory. But the other thing that we need to do is ensure that a process doesn't try to access memory that doesn't belong to the process, right? So what if the process tries to access something that is out of bounds? And so for that, we essentially add a second register, which we call a bound register. And so we compare that the virtual address is below a certain bound. If it is not, then we trigger an exception. So if the process tries to access some location over here, which would correspond perhaps to some data that's outside the process, maybe it's the kernel's data, maybe it's the data for a different process, maybe it's some free physical memory. Whatever it is, we do not want this process to access it, and so we trigger an exception if it tries to go out of bounds. And of course, a key component of this is that these base and bound registers are privileged, right? So they are under the control of the operating system, but not under the control of the application. So the application, each process, its user process, cannot access these registers directly, right? All its memory accesses are going through these registers, but it cannot modify these registers. Okay, any questions? All right, so let's see a slight extension of this technique, which actually starts having some interesting features. So suppose that instead of having a single segment for each program, we have two segments. What we're going to call the code segment and the data segment. All right, so each segment is exactly like what I described before, but the difference is that the program counter, right, so whenever we're fetching a memory instruction, we go through this set of, through the code base and bound registers, and, whenever we're doing loads and stores, we go through the database and bound registers. So essentially we're reading and writing a data segment which is independent from the code segment. So can you tell me what advantages does this separation have? What do we gain by having these two different segments? There's some good things that happen. Yes?
Well, if something goes wrong, you don't accidentally overwrite the code.
Yes, that's a great one, right? So the first benefit is, we've talked about protecting applications from each other, but there's some nice extra benefit from getting the application to protect itself from, its own data accesses. So if you have a bug, right now this separation guarantees that the buggy program will not go and overwrite some code, right? So this is essentially preventing self-modifying code. Code cannot overwrite itself, right? There's another benefit that's less obvious, and this is if you're running many copies of the same program, you can actually share the code segment across all of these, right? So you can have multiple processes, all of them which are sharing the code segment, and then you give an independent data segment to each process, right? And so that is essentially saving physical memory. Okay, any questions? So as I said, there's, yes?
How do you handle allocations to queue?
That's a good point. Next slide. I'll cover these right now. Right, so the problem here is that we're giving some fixed space to each process. And this leads to what we call fragmentation, right? Memory fragmentation. And this is sort of one of the big two problems that prevents us from using segmentation. There are two sources for fragmentation. One is programs that essentially allocate more data as time goes on. The second one is simply, if you have multiple processes that are starting and finishing over time. And so suppose that you're in this situation where you have three processes running in the machine, and they're running in these locations, right? Process 1 has a chunk of 16 kilobytes of memory. Process 2 has a 24 kilobyte chunk. Then there's this free chunk of 24 kilobytes of memory, and process 3 has a 32 kilobyte chunk. All right, so let's say we start processes 4 and 5. And at this point, we have, we allocate process 4 over here, leaving an 8 kilobyte chunk of free memory. And then process 5 runs in this free 24 kilobytes of memory. Now, assume that processes 2 and 5 finish. And so now what we're left with is the following situation. So, over time, what happens is that now we have this 8 kilobyte segment here, which might be too small to accommodate any new processes. And so as processes start and finish, we're going to be left out with a fragmented memory layout, right? We're going to be left out with a potentially very large amount of small free chunks that cannot individually support any particular process. For example, here, right, we have 56 kilobytes of free memory, and so if we wanted to run anything that had, let's say 32 kilobytes, there's no contiguous 32 kilobyte segment that we could allocate. So we would need to move, for example, process 3 8 kilobytes up to create a chunk of 32 kilobytes, and that's expensive, right? Because this example shows 32 kilobytes, but if you're talking about 2 gigabytes and moving, an entire chunk of 2 gigabytes of data from one place to another, that's very, very expensive. That's going to take a lot of latency. Another issue is, this picture shows processes taking a fixed amount of space, right? But as you asked, processes don't actually take a fixed amount of space. They start with some allocation and then they demand more resources. For example, when you're allocating data on the heap, or when you want to grow your stack, or any other number of cases, you want to give processes the ability to request more memory and get it. And so this scheme is not flexible enough for that. Okay, so to solve this problem, we're going to shift to what we call paging or paged memory systems. And so the key idea here is to divide physical memory into a fixed number of fixed size blocks that we call pages. And these pages are reasonably small. Typically, page sizes are 4 or 8 kilobytes in most systems. And so what we're going to do is translate or interpret its virtual address as an offset into a particular page and a page number. And so if this is a virtual address, we call this a virtual page number, which we're going to translate into a physical page number to produce the physical address. So we're going to have a new data structure that we call a page table that stores these translations from virtual pages into physical pages. And the key advantage of doing this is that now we can map any virtual page number into any physical page number, which means that we can store the different pages of a process, the different chunks of memory of a process, in a non-contiguous fashion. Right? And so basically, now we have this more complex translation mechanism, but we have a much more flexible mapping function. Let's see how this works with a more concrete example. So what happens is, to implement this private address space per process that we want, we have a page table for each process, right? And this page table has as many page table entries, at least in the simple design that we're going to see first, as you have virtual pages in the process. And each entry contains the physical page number for the virtual page number of that particular process. And so, for example, in this particular case, we have 3 processes, all of which have this second page over here, right? Let's say that there's some virtual address VA1 over here. And so, to translate this virtual address 1 of process 1, we access entry 1 of the page table, and that has a pointer, right, that is pointing to some location in physical memory, to a page of physical memory. This page in solid blue over here, right? Now, for process 2, the same address, we're going to go to the same location in the page table, and now you see that it's pointing to a different location, right? And same thing for process 3, right? It's pointing to a different location. So now, note that the pages of process 1, the pages of process 2, and the pages of process 3 are all stored non-contiguously, right? We just have a bunch of 4 kilobyte chunks which we're allocating independently. And so we don't have this restriction of having a big chunk of memory for each process anymore, right? Yes?
So I'm curious about what happens when a process has finished using a particular page. Does that particular page in physical memory get tagged as, oh, I'm free, if a next process needs space, this is where I go?
Right, so apart from the page tables, the kernel needs to keep some sort of free list, right, some list of available space, and then it's going to allocate from there.
Okay.
Yes?
Why do some page entries point to free memory? Shouldn't they point to something used by a subset?
Yeah, this actually is a poor choice of colors. So what happens is this free pattern is slightly different from this one and this one and this one. So I'll fix this in the handout. Sorry?
So nothing's pointing to a free.
Nothing's pointing to a free page. Yes?
Great. Where are the page tables located?
Great question. We'll see that in a minute. For now, assume that they're somewhere, we don't know yet.
Yeah, I was going to ask, the white page tables, those are done by the operating system, right?
Right. So the key thing here is these page tables are under the control of the operating system, right? That's the key technique here. Otherwise, we would allow processes to alter where they point, alter what physical memory they're accessing. And so all of these translation mechanisms are always under the control of the operating system. Okay. We're going to see a few more examples of page tables and address translation. But at a high level, let's look at the pros and cons of paging versus segmentation, and start getting into the issues of paging. So, as I said, the good thing about paging, right? The obvious good thing about paging is that now you don't have fragmentation, right? So now we don't have this issue of having to move large chunks of memory. Can you think of another benefit? Yes?
I think you don't need contiguous sequences in memory.
Right.
It just depends on what's free, and you can determine that with a relative ease.
Right. So because you're managing everything in fixed size blocks, right, management of physical memory is much easier. But this sort of falls under the avoids the fragmentation issues. So this goes back to what I mentioned at the beginning, that the second big feature that we want from virtual memory is to use main memory, to use DRAM as a cache for disk. And so what if we design our system so that we design our page table so that it could say, well, this is pointing to some location in memory, or for some virtual pages, it could just say, it's not here, it's somewhere in disk. I just don't have it. If you want to access this particular page, go get it from disk. So that's precisely what demand paging, the technique that we're going to discuss next, gets us. The ability to use main memory as a cache for disk. Okay, so of course this comes at a fairly, with a very large caveat. So we've gone from using two registers, right, a base and a bound register, to using a page table. And these page tables are big, right? They're much larger than the base and bound registers. Which brings us to the obvious question, which is, where do we store these page tables? Right? Clearly not in registers. We're talking about at least megabytes of storage here. So they're not going to be in registers. So what makes sense is to have them in main memory. To have the page tables themselves in main memory. Right? So to access main memory, you first need to access main memory. Okay, so here's how it works. Right? First of all, the kernel is going to have some array that stores that stores pointers to all the page tables, right? It stores the addresses of all the page tables of all the running processes, right? And then we're going to have, at this particular address, for example, at this starting address, we'll have the page table for process 1. At this starting address, we'll have the page table for process 2. And so what we're going to do to do a single access is, we'll get the virtual. We essentially divide the virtual address into the offset and the virtual page number. We take the virtual page number, add it up to the base register of the page table of the process that we're currently running. In this case, let's say we're running process 1, and this will give us some memory address which we're going to access to get the physical page number and therefore produce the physical address, right? And in this particular case, this will have different the addresses of the different. Or the physical page numbers, which basically is the address of the different pages of physical memory that hold our virtual pages. And so in this particular case, let's say we go through here, right? So we'll get to this particular page over here, right? And so then we'll use the offset to figure out which word we need to access within each physical page. So basically, different page tables are going to have pointers to different, are going to have different physical page numbers. And then, as I said, this array over here is going to store the starting addresses of its page table, right? So then, its translation is basically one memory access to get the physical page number, and then one memory access to get the data at the physical address that we want to access. And by the way, all these arrows here essentially are physical addresses, so we're not doing virtual to physical address translation in any of these. Because you have multiple processes, the last piece of the puzzle is that on a process switch, you need to change this base register to point, if, for example, we deschedule process 1 and schedule process 2, we would have to change the base register to point to here so that we get the right translations. Yes?
So I think you said earlier that we have the same number of pages in our page table as pages in a particular process, right? So how, don't we run into the same issues as before of like allocating a certain
Absolutely. And so what we're going to do to simplify our lives for now is assume that you have all the virtual address space. So for example, if you have 32 bits of virtual addresses, right, assume that your page table has one entry for every possible virtual page number that you can have, that you're not restricting it in any way. And that's, in fact, how the simplest possible page table organization works. Right? So for every possible virtual page number, we're going to have a very large array that has an entry, right, for each possible virtual page number, right, that gives us the physical page number, or it just says, it's not allocated or it's not here. Right? Yes?
Wait, is the virtual page number part of the, I guess, the virtual address of the program?
Yes. So we're going to go from the virtual address, we're going to get the virtual page number, which then we're going to go through the page table to get the physical page number, which then we're going to append the offset to get the physical address. So it's a multi-step process. Okay. So the key issue here is that accessing one piece of data, right, each memory reference is now taking two accesses to main memory. And so in the rest of the lecture, we're essentially going to address these efficiency issues and look at how demand paging works, right? So these two main issues. The first one is, how do we reduce this overhead of memory accesses, right? So we want to have these paging based systems that are very flexible, but at the same time we want them to be fast and we want them to not take a ton of space to store the page tables. So we'll see how to do that towards the end of the lecture, but first we're going to address the issue of what if we cannot fit all the pages in DRAM? What if we cannot fit everything in main memory and we need to use secondary storage? Now, there's a couple of issues that are quite interesting. What if the page tables cannot fit in DRAM? We're not going to see this in W4. If you're interested in these, there are more advanced courses that will teach you, some of the rigmaroles that you have to go through to store the page tables outside of DRAM. Okay, so let's see these in more detail. With demand paging, and so now we're getting to the specific organization of the page table. The key idea here is that because not all the pages fit in main memory, we're going to use some part of disk, which is much larger than main memory, as storage for main memory pages. And so we call this swap space, and we'll see why it's called swap space. It's because we're always swapping pages between disk and main memory. So the page table is just an array of page table entries that's indexed by the virtual page number. And then the page table entry, so each entry, which we call the page table entry, contains a resident bit to tell us, is this page in DRAM or is this page on disk? And then if it's resident, it has what we call a physical page, the physical page number for the memory resident pages. Otherwise, we're going to have a disk page number. We're basically going to point to the location in the swap space on disk that has the page that we want. Apart from this, there's some protection on usage bits. Things like, has this page been written to, right? So that we need to write it back to disk if needed. Or can this page be written, right? If it's code, maybe you don't want to allow programs to write to that memory. And so again, the way this works is, you start from the base, the page table base register, right? That gives you the starting address, taking the virtual page number as the offset, you use it to index the particular page table entry that you're interested on. In this case, we have a translation to a physical page number that gives us some location in physical memory, and then we take the offset to figure out which particular word within this page we want to access. Right? So one nice thing about this is that even if everything fits in memory, demand paging allows us to be lazy. So suppose that you have a program that is 100 megabytes of code. But when you run it, it doesn't do much, right? It's just looking at the input and saying, I cannot process this, it's perhaps throwing an error. So you don't really want to load in the whole program, right? Run 10,000 instructions and then bail out. And so what demand paging allows us to do is initially have everything to be resident on disk. And then as we execute the parts of the code that we care about, we're going to be bringing them to memory on demand. Okay. Any questions? Yes?
In the jargon, what's the difference between disk and DRAM and memory? And it's difficult to keep.
Okay, so when I mention main memory, I'm always talking about DRAM, which is this dynamic random access memory technology that gives you, accesses in about 100 cycles, but in current technology you can have a few gigabytes of it, right? When I say disk, this can be either a hard drive or a solid state drive, right? So this is HDD or SSD. These take, the solid state drives, which are more common today, are flash based. They take about 10 to 100 microseconds to serve a read operation. So we're talking about 2 orders of magnitude, 3 orders of magnitude worth of difference to read some data. And a hard disk is basically a spinning platter that's read with a magnetic needle. It's pretty old at this point, but it's still used because it's very dense, but it's really, really slow. We're talking about 10 milliseconds per read. And so there's this whole hierarchy of storage technologies that essentially, we saw a glimpse of in the memory hierarchy lecture. Okay. Any other questions? All right. So let's see a more concrete example. And in particular, let's use something that has small virtual and physical addresses. So, in general, in your RISC-V processors, you'll have 32-bit virtual addresses. But here, let's assume that we have a system that has just 256 bytes per page. So we are going to have 8 offset bits, and then 16 virtual pages, right? So that's 2 to the 4. So overall, we're going to have virtual addresses that are 12 bits, right? 12 bits is just 2,000 locations. It's not very big, but some systems actually use small memories. And then we're going to have physical addresses that have, so this is the actual amount of physical memory that we have. We have 8 physical pages, 256 bytes each, so we have 2 kilobytes of memory, right? And so again, we're going to have 12-bit virtual addresses, 11-bit physical addresses, and because all of these numbers are pretty small, we can actually put the entire page table here, which has 16 entries, right? It has 16 entries because we have 16 virtual pages, right? So 1 entry per virtual page. And then we're going to have 8 physical memory pages. So here, right, some entries are populated, there's 3 bits here, the dirty bit, the writable bit, and the resident bit. So D, W, R. And for whatever is resident, like this entry over here for page E, right, we have a pointer to a physical page number, right? So it's saying physical page, this virtual page number E maps to physical page number 5. Yes?
Is the DRAM also a cache?
The DRAM is not a cache in the sense that there's no hardware, there are no hardware tags, but it is, we're using it as a cache thanks to virtual memory.
Okay, but it's not like hooked up to the other caches, like SRAM?
It is in the sense that misses from those other caches are being served by main memory.
Okay.
We will actually talk more about the interaction of caches and main memory in the next lecture, but for now what we're going to do is assume that you just have the CPU and memory. Okay? Yes? So writable bit implements something that's similar to the protection that we saw when you have to separate segments. So for example, when you have code, you don't want anyone to write to it. And so you'll mark that page not writable, so that if you have a store to that page, you'll trigger an exception. Okay, so let's say that, let's assume that you have a load that issues an access to virtual address 0x2c8. And so what is the virtual page number for this virtual address? Right? We'd want to translate this virtual address into a physical address. The first step is to divide it into the virtual page number and the offset. Right? And so in this particular case, it's very nice because everything's a multiple of 4, so that's 1 hex digit. So the virtual page number is 2. And what physical page number, what do we do with this virtual page number? Well, we go to location 2 in the page table, right? Page table entry 2. So here we see that this bit, the resident bit, is set to 1, and the physical page number is 4, right? So our physical page number is 4. And therefore, this corresponds to physical address 0x4c8, right? And so now we can go and access memory at that particular address. Okay, so we've seen what happens when you have data actually in memory. But what happens when you miss, right? What happens when you hit on a page or a virtual page number that's not actually resident, that is on disk? So there are lots of similarities between the process that we're going to see and caches, which we've seen a few lectures ago. And so here, the setup that we've seen so far is we have a cache and then main memory or primary memory, and the setup that we're going to see today is we have primary memory acting as a cache for the secondary memory, which is on disk. And so, as I said, the concepts are very similar, right? So here we talk about a cache entry, here we talk about a page or a page frame, we talk about cache blocks, here we have pages, right, which are also large so that we can amortize the overheads of keeping all this metadata. There's cache miss rate, there's page miss rate, cache hit, cache miss, page miss. But there are differences here, right? A cache miss, in this case, it's served from this DRAM primary memory, and so it takes around 100 cycles. A page miss here means that we need to go to disk, and disk is going to take milliseconds to reply. Or at least if you have a solid-state drive, it's going to take hundreds of microseconds. And so we're talking about hundreds of thousands to millions of cycles. So since misses are so slow, it actually doesn't make sense to handle the misses in hardware. So what we're going to do is design our system to handle the misses in software. And that's simpler. And it's actually not any more expensive than it would be to handle them in hardware, because we're going to be waiting for the data to come back anyway, right? If we're going to wait for 5 million cycles, what does it matter that we spend 100 instructions processing the miss, right? Why not just do that in software, which is more flexible? Okay, so here's what happens, right? And again, what we're going to do is resort to exceptions. So when the CPU issues an access to a page that doesn't have a valid translation, that's not resident, this actually causes an exception. It triggers what we call a page fault or a page fault exception. And that, again, invokes the OS, and the OS is going to handle this miss, right? And so let's see first, before diving into the details, what the state in the system is before and after servicing the page fault. So before the page fault, suppose that the CPU wants to access this virtual page number here, virtual page number 5, which is not resident, and so it's pointing somewhere on disk. And so the OS is going to have to choose something to replace it with. In this case, let's assume that it's this virtual page 1, which is resident and is pointing somewhere over here. You're going to have to implement some replacement policy. Let's say that you have least recently used, and this page is the one that was accessed the least recently, the least recently accessed page. And so after the page fault, we're going to have the following setup. First, the OS is going to write whatever contents of the virtual page here, virtual page 1. It's going to evict that page to disk. right? And then it is going to load the page, virtual page 5 over here from disk to the location where virtual page 1 was. And then it's going to alter the page table so that now virtual page 1 or page table entry 1 points to disk, to the right location on disk, and then we, for virtual page 5, we're pointing to the right location in main memory. Right? Essentially, we've swapped the pages, the locations in disk and main memory. So the way this happens is the same process as on this, right? Describe essentially exactly what you implemented on Lab 6 for a cache, but in software, right? So basically, the operating system chooses a page to replace. If it's dirty, it writes it back, and then it marks the page table entry as that page is no longer resident. Then it reads the page from disk into the available physical page, and then it updates the page table to show that the new page is resident and has the right page number, right? And finally, as with all exceptions, once we've done servicing it, we return control to the program, which re-executes the memory access, and now this memory access is going to go through here, through the page table, find a valid translation, and actually complete. Right? Yes?
Why is this better than just loading the VPN5 from disk and not doing anything else?
Well, because in general, the reason that you have VPN5 on disk is that you're out of physical memory. So every entry here, right, is, although not all mappings are shown, every entry of physical memory is used. So you have to pick something to replace. Of course, if you had a free physical page, then you would just go, use a free physical page. But in this example, we're assuming that you don't have any free physical pages. Okay. All right. So this concludes our discussion on demand paging. Now remember, there are two other issues that we need to take care of. The first one is, and these again are performance optimizations, but are very important performance optimizations. The first one is that it's completely impractical to have two memory accesses, or at least two memory accesses per reference, right? We don't want each page table access to be a memory reference. And so what we do is actually we introduce a cache for the page table. And this cache for the page table is called a translation Lookaside buffer, or TLB. But despite this fairly complicated name, it's just a cache. It's a cache where the tag is the virtual page number, and then we're going to have all the same bits that we have in a page table entry. We're going to have a physical page number, we're going to have the resident bit, the dirty bit, the writable bit, and so on. And we're going to have a valid bit just the same way that we have a valid bit in our caches, right? So this is going to be a small cache, right, that for every memory reference, we're going to first access this cache, see if we have a match, and if we have a match, then we can perform the translation in a single cycle without going to memory. Otherwise, we have to go access the page table and fill the right state in the TLB, right? Essentially fill in the new translation in the TLB. Okay, so we have a cache for page table entries. Now, these caches, as I said, are typically small, so they're 32 to 128 entries. They don't store a lot of translations, so that they can be very, very fast. In fact, modern processors have multiple levels of TLBs, just like modern processors have multiple levels of caches. And then, there are two details that we need to take care of. The first one is that when you switch from one process to another, right, the operating system, if you don't do anything special with the TLB, actually needs to flush the TLB, right, because the TLB is now holding, it's caching page table entries that are stale. So you have this problem of staleness, and we could actually solve this by including the process ID in the tag, so that we can have context switching among multiple processes, and we only get a match if the process ID matches, the process ID matches and the virtual page number matches. So some systems will do this, and then there's another big design decision, which is what happens on a miss? And here systems will all systems need to check the page table, which we call walking the page table. And the key question is, well, how do you do this? You could do it in hardware, you could do it in software. It's not that frequent, so it's okay to do it in software. But in fact, usually most modern systems do it in hardware. So they have what we call a memory management unit that issues the access to the page table in hardware and avoid taking an exception. But you could take an exception, and there are other architectures like MIPS that do this in software. But in particular, RISC-V and actually x86 do these page table accesses in hardware. Okay, so at this point, there's a lot of design decisions. Let's go back to see how this all fits together. And so the program is issuing virtual addresses, requests or references with virtual addresses. So the first thing we're going to do is issue a lookup to the TLB. See if we have a translation there. Best case scenario, we have a translation. Now, even if we have a translation, we need to figure out whether we can actually perform the access. For example, if this is a store and we do not have write permission to this page, then we need to throw an exception, right? And so if we pass the protection checks, we basically have the physical address and then go directly to memory. If we hit one of these, the translation is there, but actually you don't have the right permissions for it, then we cause an exception. We trigger what we call a protection fault. Okay, so the other path is if you have a miss in the TLB, so your translation is not in the TLB, now you need to do a page table walk, which we said can happen either in hardware or in software. We will do it in hardware. And then there are two options. Either your page table has the translation, in which case we go and update the TLB and we have the right physical address already, or it's not in memory, in which case, again, we need to trigger a page fault so that the operating system can load it from disk and have the right translation, right? And insert the right translation in the page table, and then we'll replay the memory access, we'll replay the instruction, and we'll go through this other path over here, right? Okay, so let's finish off with an example that actually makes this much more concrete. So suppose that you have a virtual memory system that has 4 gigabytes of 32 bits of virtual address space, but you only have 2 to the 24 bytes of physical memory. So that's 16 megabytes, right? And we're going to have 1 kilobyte pages. Not only that, we're going to have a 4-entry TLB that's shown here. And so first, some questions about how many pages can be stored in physical memory at once? Well, you have 2 to the 24 bytes. You have 2 to the 10 bytes per page. So 2 to the 24 divided by 2 to the 10, that's 2 to the 14. So we can have 2 to the 14 pages in physical memory. Now, how many entries are there in the page table? So we have 2 to the 32 possible byte addresses and 2 to the 10 bytes per page. So that's 2 to the 22, right? You divide both to get 2 to the 22 virtual page numbers. Yes?
Can you walk through the calculations for both of these again?
For which one?
Both of them. How did you get to the
Okay, so this is because we have two to the 24 bytes over 2 to the 10 bytes per page. That gives us 2 to the 14 pages, right? So this is bytes per page this is physical memory bytes. So this is physical memory pages, right? Same thing for this one, right? Except that now we're considering virtual memory bytes. Okay, so you can go through and answer some of these questions about how much storage is this taking. You know, we have 14. We're gonna need 14 bits for the physical page number and 2 bits for the resident and dirty bits. So we're gonna have 16 bits per page table entry. So you can compute the size of the page table. But let's do one of these examples of what is the physical address for virtual address 0x1804. So if you take 0x1804, again, the first step here is to compute the virtual page number. Now here things are not so nicely aligned. So you put it in binary. This is your offset, right? And these bits are your virtual page number. And what is this? Virtual page number 1106, right? And so what components are involved in this translation? Well, so we go to the TLB. Do we have a translation for 6? Yes. And what is the physical page number? 2. And so given that, you can go back and compute the physical address for this virtual address. And in this particular case, you only had to check the TLB, right? Because you already had a valid translation. For some of these other ones, you'll see that you actually need to go to the page table, and in one of the cases, you go to the page table and you actually don't find a translation. Yes?
With this one, does the page table take up half of all the memory?
Yes. Not a very efficient design. And so we'll see how to fix that at the beginning of next lecture. Yes?
So why do we need like a TLB in this case? Because VPNs are ordered from 0 to like whatever number.
Right.
8 in this case. So why can't we just access the 6th row with index 6 in constant size?
You absolutely can access this row. The problem is that that would take you an extra memory access, and you don't want that. That's why we add the TLB. Because this page table access is very expensive, right? This TLB access we can do in a single cycle. That's why we have this very small cache.
Oh, because that's the like extra memory.
Right. This is a performance optimization.
So TLB is in the CPU cache.
Yeah. Great question. We'll discuss this next time.
Okay, but the
There's-
idea of the TLB is lots of memory.
Assume that there's no cache, and so you access the TLB before main memory. The TLB is typically before the cache, but we'll see this in detail in the next lecture. All right, that's it for today. Tomorrow, on the next lecture, we'll actually start discussing how virtual memory interacts with caches. All right, thank you.